So we're going to start off with a simple example. We're going to start off with a more simple version of replication. We're going to look at bacterial replication. So as you may recall, bacteria are circular. Their DNA is circular. And so DNA replication initiates at a single spot in the circular DNA, and then the replication forks proceed bidirectionally. That is, they proceed in both directions around the circle. So as it's being replicated, you end up with this particular structure where you have two new circles forming out of the original circular chromosome. And the process of replication proceeds at about 1,000 nucleotides per second. That's very fast. But remember that there is the issue of supercoiling in bacteria. And so they have a number of proteins that allow them to supercoil and unsupercoil their DNA. And so in the process of synthesizing new DNA, there are these proteins called helicases. What these helicases do is they unwind the DNA as the DNA synthesis proceeds. So the parental DNA is unwound by these helicases. But in the process of unwinding the supercoiled DNA, you introduce more supercoils in the forward direction. And so the complementary protein to helicase is DNA gyrase. So we can already see that there's this complicated push and shove from the process of replication, whereby the unwinding of DNA leads to supercoiling ahead of the replication fork, which needs to be unwound by the DNA gyrase. And this DNA gyrase is particular to prokaryotic replication. We don't have this problem in eukaryotes. And so while helicase is present in both eukaryotes and prokaryotes, DNA gyrase is present only in bacteria. Thinking for a moment, think about how you could use that to create a new antibiotic.